Hello and welcome to lecture 15 of machine learning from data. And in this lecture, we are sort of trying to put everything together, everything in perspective. We are trying to reflect on our path such that whatever we've done so far, so we are going to do some kind of like looking back at that and um, kind of trying to condense everything that we've learned so far and try to understand whether we are going to like we can make some sense out of it or not and how we can apply things and how to go forward. So that's the focus of today's lecture, what we did. The machine learning zoo, this is an important aspect. This is coming up because this question comes up again and again despite all the theoretical analysis or despite all the theoretical derivations that we've done until now. This comes up that there are these like keywords, these buzzwords all around, right? And so how do those fit into whatever we have done until now, and what are we going to do like going forward? So we are like at the somewhere in the middle of our path, and we have spent enough time in theory, and so how do we take the theory forward and go from here? So that's the fundamental idea behind this lecture, that let's kind of take a break somewhere in between, sit down and reflect on our path and try to see how can we move forward. So that's what we're doing in today's lecture. And so there is nothing new that is going to be that we'll be talking about here, but we are going to do some kind of, as I said, reflection. So it's a more of a relaxing lecture in the sense that there's nothing new that's coming up, but we're just like kind of repeating things and then putting things in perspective. So let's move on. Quick recap of the previous lecture, because previous lecture was extremely important. It was an important lecture, again, that condensed our theory in such a way that I pointed to three important learning principles. The first one was related to the model itself, and the other two were related to the data. Right. So what did the first one said? The Occam's razor said simpler is better, and then we came across something that's known as falsifiability. So what was that falsifiable hypothesis or falsification? We saw this like really nice example that demonstrated what falsification was. So we were trying to establish this hypothesis between resistivity and temperature, and scientist one provided no evidence that this data could falsify the hypotheses, because there is no way you can not join 2 points by a straight line, right? So there is no evidence of falsification, and we found out that the evidence of falsification in itself is so important, like it's inherent in the machine learning problem, such that it plays an essential role, right? So we found that if a simple hypothesis, right, can shatter, or like if we can fit a simple hypothesis into a given data set, that means that's the element of surprise, because like theoretically speaking, there is a very small chance of that happening. So that's what the idea of Occam's razor was: simple is better, and then falsifiability. The second thing that we talked about was sampling bias. So the first thing, we need to make sure that the training and the test come from the same distribution, right? If not, then at least we have to acknowledge or account for it, right? So do something to account for it if that's not the case. But the basic idea is that we are making predictions, we are making some statements about some problem, and so the data has to come from the same sample. Otherwise, your estimates will be from some other bin, and then your data is from some like other bin, and so the estimates are not really a reflection of the data that you have. And the example that we looked at was the Truman Dewey um, election results in, I think, 1948 US election results, and how Chicago Tribune reported a day before the results were supposed to be out that Truman is going to be defeated. But that wasn't obviously the case. As you can see here, Truman holding that newspaper, like really happy, showing that how this was not true. And the reason being that the sample that was collected was already biased, right? So we saw that example in the previous lecture. And then finally, one very important thing, data snooping. And data snooping is important not just because, first of all, theory tells us we shouldn't be looking at the data before selecting our hypothesis set, but then of course, like at some point when applying machine learning as machine learning practitioners, we have to make that choice, because it is the data depending on which we make that choice. So essentially, it is my data on which my hypothesis set is applied, and then I pick up that final G, right? And so there are two things that we have to take into account. First of all, when we are checking the like how good my hypothesis is, right? So if I'm checking like how well this is, I'm assessing the performance of this, then I should try to use data without this contamination. So that data shouldn't have participated in the selection of G, first of all. So that's why the idea of test set comes into picture. That's the first thing. And then the other thing is that we should know, like we already know theoretically that there is a price of choosing that G, and that has been already incorporated the theory that we built. But as you increase that choice, and so this is what this picture is showing, right? So basically we have this path of going from D to G, and that path depends, right? I can take different paths, and I can have like multiple choices throughout. Maybe that choice is made by me, or maybe that choice was made by different people at different points in time, and I'm trying to utilize that to arrive at G, and so on. So those choices could have been like, could be happening anywhere. The point is, the more the choices you have, right, the more the penalty you pay. So you are charged for every choice. So the thing is that whatever predictions, whatever assumptions, whatever outcomes we are expecting out of our G, our final hypotheses, we have to take that with the pinch of salt, in the sense that like every choice that I've made in order to arrive at G has somehow incorporated in it some kind of penalty, like direct or indirect. So sometimes data snooping can be like really subtle, that like we saw when the data is normalized altogether, and then we are applying, then we are splitting test set and our training set, and that has impacted my data, that has impacted my decision for G, and so that's not a good thing, right? And so that was data snooping, and basically what we were saying was, uh, in like model selection, simpler is better, falsifiability should exist. And so sampling bias, we were talking about the data being sampled, like the same bin should exist. And then in data snooping, well, you pay the price for every choice, and so be aware of that. You cannot look at the data, and if you don't, that's better, right? Because like the more you get into that, the more you deviate from the theory. That's the idea. Okay, so these were the three important learning principles. Again, they stay with us throughout as we even move on to more advanced techniques. So let's look at what's today's lecture all about. So as I said, today is more about like reflecting on our path until now. And so what have we been after until now? We've been after prediction, right? In general, predicting something, like going after unknown. And whenever you go after something unknown, it is hard. It is bound to be hard, because there is no like magic that exists, right? And so like when we are predicting, all we have is our data, right? So all we have is the data, and obviously we have techniques to use that data to predict something in the future, or to predict something that's unknown, and that is going to be hard. That is going to be hard in its own ways. But looking into what we are doing through machine learning, is we are trying to look into the future by looking at the past, which obviously cannot be that straightforward, right? It's like you're driving a car and somebody's asking you, make your decisions of like going forward by looking at the path behind, which is not like that straightforward. Maybe that can help in certain things, but not exactly, but not quite. And so that's why we spend so much time building our theory, right? And then we came up with some pointers. But again, there is no go-to solution for looking into the future. But there are things, there are techniques, there are ways that can make that journey towards the future a little better, a little like you can get a little comfortable. So, for example, easier done in a simple setting. So we can look into the future if the environment is as simple as it can get, right? And so we've talked about that a lot, why and how and so on. But the more data you have, the better you can look into the future, of course. But then that comes with a price and other things. Of course, we are aware of that as well now. And so, of course, remember the price we pay when making choices. So moving forward, including data, the more you're making choices with your data, you're paying a price as well. So looking into the future is not that straightforward. It's not like, okay, get more data from the past, get more historical data, and then you're better off. So that's not the case as we know right now, right? And all we care when we are doing machine learning is what is going to be the future, what is going to be that test point, how is that test point going to behave, and that's all we are after. And again, like this goes back in circles, I would say. So it is hard. It is going to be hard. Nobody said it's going to be easy. And that's why we have this whole course. And we are working towards making it doable at least, right? So prediction in general is hard. Always remember that. All right. So having said that, what was our plan when we started with the course, and how are we going to go forward? All right. So our plan was, and this, by the way, like these 5 things are like, I will write it down, the foundations, the theoretical foundations that we've built until now, right? So these are theoretical foundations, and then we will move on to this part pretty soon. So what did we do until now, right? So the first question that we tried to answer is, what is learning? And we defined that learning is something such that we are able to come up with a final hypothesis G, which is as close to my target function, which is the unknown part, right? Because remember, we are after that unknown. So we are trying to come as close to that unknown as possible after looking at the data, meaning after utilizing whatever input we have, which is data essentially. So that is how we define learning, right? Based on, obviously, like this is like you have the data, you come up with a final hypothesis based on some hypothesis set you have in mind, and then like just come with that G that is as close to F as possible, right? So all of this is good. How can we come? Like, can we do it? Like, is it possible that I will come close to G, like I will come close to F or not? That's the second question. So then the second question was about feasibility of learning, which kind of took us to this 2-step learning process. So we were trying to answer this question of like, can we do it? Okay, we defined this is learning. All of that is good, but can we do it? Well, a short answer to that question was yes, provided that the data that we are working with is IID. There's certain assumptions, right? The IID, and then there is a possibility of failure that also exists, right? And we cannot say for sure, but probability came to our rescue, and we said, yeah, probabilistically, yes, right? So probability came to our rescue, and we said yes. All right. So of course, we cannot say for sure, but probabilistically, yes, with certain assumptions. And finally, we came to something that is like 2 learning principles, 2-step learning process. And the first step was that you get E in close to 0, right? And but like we kind of said this was the first step and this is the second step. So let's stick to that. So E in should be as close to E out as possible. And so the relationship is through the like VC analysis, right? And so the relationship had this term of complexity, which was a function of the VC dimension and large n. So we know now that a higher VC dimension, with a higher VC dimension, we pay the price of model complexity. And so a simple hypothesis made this bound that we had, or the relationship, tighter, right? So that was the first thing. And then how do we ensure that this is small as well? We ensured that using E in being like really close to 0. So amongst like whatever hypothesis set we have, choose a good hypothesis using the algorithms. And we've looked at these algorithms, like a few of them at least, how to have E in close to 0. So that was like, yes, can we do it? Probabilistically, yes, with certain assumptions through a 2-step process. So that's how we answered that question. Coming to the third question, okay, can we do it? What is learning? All of that is good, but how to do it? Because that's like the most important component of learning. And so how to do it, we talked a lot about linear models. In fact, so much so that we said that most of the machine learning problems can be categorized into 3 types, remember? And then we looked at it through the lens of the credit card analysis. And then we said like linear models can solve almost all problems. We looked at the linear regression type of problems rather, I would say, classification and logistic regression. And then we also saw what happens when we had like some non-linear type of data. How can we do the transformation and still solve those problems using a linear model? So that was what nonlinear transform was doing. And some of the important algorithms that we've looked at is PLA plus the pocket algorithm, which was allowing some kind of error, then the pseudo-inverse 1-step algorithm that quickly solved for regression, and then our very nice gradient descent. And we saw how iteratively it went to that nice minimum function, because we came up with the error function that was really smooth and was convex, right? So all of that, this is how we do it. So these are the techniques that help us do it, right? Okay, so doing all of that was fine. It was good, I would say. Doing all of that is great. But then we found that there were certain issues with doing it, and so we wanted to do it well, right? And so to do it well, we have to look at what are the issues that are making us not do it well. So the most important issue is overfitting. It's always there because noise is always there in your data. You cannot get rid of noise. There could be two types of noise, stochastic and deterministic, and there is no way we can get rid of it. But then we can of course apply, so if this is a disease, that's what we said, if overfitting is a disease, then we can cure it using something that's known as regularization. So there are two ways to kind of control it. One is regularization, one is validation. If you remember, regularization was kind of putting a leash on your algorithm and not letting it go astray because of noise. That was regularization. Validation was doing a direct estimate of E out using using different techniques that we applied on the data, and then we improvised that because we saw there could be some issues with validation, and so we did cross validations. All of those techniques were really well because they helped us improve what we did with the models and the algorithms. All right, having said that, finally we came to this like really condensing lecture, I would say one of the best, because it put everything into perspective, and we said the general learning principles have to be Occam's razor, sampling bias, data snooping. When looking for the model, look for the simple one. When looking at the data, know how to get the data, right? So such that your data is free of any kind of bias, and then know how to handle the data. So do not look at the data before you fix your hypothesis set. All right, and we also saw the downsides of like what happens if we don't take care of these things. Okay, and all of this put together goes back to our larger question of like prediction is hard, and this is how we do prediction. This is our plan, and if we stick to the plan, most likely we are in a better position to answer like or get a prediction on our test point. Okay, so all of that, we are done with foundations, we are done with the theory, and we are in a position to kind of apply this theory to more sort of complex settings, and that's what we are going to do. So we are going to move on to advanced techniques and other learning paradigms. But before that, let's look at what, like many of you have asked before, whether we'll be doing this or that or not. And so that's what the jungle I was talking about is all about. So learning from data, it's a jungle out there. That means we have all these buzzwords around, essentially a zoo of these terms. I am pretty sure all of you have heard like what are GANs and I don't know, RBF, SVM, deep learning. It's all the time there, big data. So we have like looked at some of these terms and we are now very much familiar with them. There are some of these terms that we are going to look at, obviously, but this is beyond the scope of any one course that can like go over each of these, right? So it's like next to, I would say, impossible, but yeah, we'll try to. But of course, if you are good with the theory, if you understand the foundations, because almost all models will have like similar foundations. So when you understand that, it's not that difficult for you to like transition to any of these applications at all. But now, because we have all these buzzwords around and we have these models available everywhere, and so we'd really like to know, and from the perspective of like what you would like to know is like how are we going to proceed forward given all of this already there. And so what we decided to do was to separate these buzzwords like somehow into some categories based on some criteria, right? Because definitely this is something that's like overwhelming. So let's put everything into perspective and see what's going on, what and how, right? So all these buzzwords essentially can be categorized into three important, I would say, sections or categories, right? So the first one is theory, the second one is techniques, and the third one is paradigms. And believe it or not, one like all of these buzzwords fall under one category or another. For example, if we are looking at this, like VC analysis, whatever is in bold is something that we have looked at. Whatever is underlined is like means that we are going to look at it. And if it is like italicized, for example, this or this, maybe if we have time, we're going to look at that. So that's how this has been segregated to kind of pave our path for the future. for some of the future lectures, essentially. So we've looked at VC analysis and bias variance. That was the most fundamental part of our theoretical analysis. And why is it important? It's important because it's relevant to practice and it's completely general, right? So both bias variance and VC analysis, and we've looked at that. But of course, theory comprises of other things as well. So for example, the complexity theory, for example, the Bayesian models. So the Bayesian models is that's another important buzzword that you might have heard a lot, right? The only there's a slight kind of variation in the way we have looked at theory versus how this Bayesian models look at theory. So they actually assume that there is some prior distribution for the target function, which leads to some really good results because we have, on the other hand, maintained that my target function is completely unknown, right? So our theory becomes general, completely general, because of the fact that we've maintained that my f is unknown. But in like Bayesian models, there is that assumption that it comes from this particular distribution, and then obviously the complexity of like mathematical complexity of proving and getting like good results for the Bayesian models goes down because you already have some assumption on the prior distribution of your data. So that's how the Bayesian works. And then there are other theoretical. So SRM is one of them. And so this is also known as structural risk minimization. It takes a slightly different approach in how we did with the VC analysis versus this one. It's a more statistical kind of approach. So all of this like theory exists, but as long as I think we have the most general in like theory and the most general models in our toolkit, so to say, I think we are good, right? We can understand everything going forward. Okay, so that's the first category. The second category is the techniques. So the techniques that we apply. Okay, so techniques are further split into two parts: models and methods. So why are models and methods like categorized differently? Well, models are, for example, we looked at the linear model, right? So how we look like what hypotheses we'll come up with, right? And then how we are going to like the algorithms as well, right? So how we are going to get or solve that, right? That was the linear model, very powerful, if you remember, especially like with good features. It did like excellent and all of that. So it's just one of the most fundamental models, always be there with us. And the methods are like kind of a step forward on models themselves. A method is a technique applied to all models. So this is like more general in the sense that I can apply regularization to linear models and neural networks, right? And similar to that, like validation can be applied to different types of models. So there is like no restriction on what methods can be applied to what models mostly, right? So that's that. Aggregation is a technique to combine different models and sort of try to get their benefits, right? So aggregation is something that we're going to look at. Aggregation, as I said, puts together multiple models and then try to derive the benefit out of all of them. Pre-processing is something that we've looked at a little bit. For example, the digits data we talked about, remember we said this is already pre-processed. So somebody already got the handwritten digits from like the US Post Office, and then they converted it using some computer vision algorithms, and they pre-processed that data for us to analyze, right? So that's what pre-processing does. All right. Then finally, the third category, right? And so what is this third category? Basically paradigms. So I would say if you don't like really relate to paradigms right away, this is nothing but a framework, I would say, right? So different frameworks of learning. We have looked at supervised. Supervised, as you know, is like something they are most prevalent, used a lot, I would say. Best performance usually because you see something that you're trying to learn, which is usually easier to learn. With unsupervised, on the other hand, you're trying to like organize things, and then based on that, you're trying to learn, and based on that, you're trying to predict, or based on that, you're trying to come to certain conclusions. And it has been seen that like supervised and unsupervised together can have their own benefits in certain situations, right? So unsupervised is like really helpful for the supervised learning and is good on its own as well. Okay. So what is this reinforcement learning? And I've had this question like multiple times. So I'm not 100% sure if we will be able to cover this, but we'll definitely try to touch that. It is nothing but an area of machine learning where there are agents that take actions in a certain environment, and basically there is this notion of reward and penalty. So it's like one of the basic machine learning paradigms, I would say, along with supervised and unsupervised learning. And it differs from supervised learning in that it does not necessarily need labeled data like input output pairs like we have in supervised learning. The focus is to find a balance between like something that's unknown and whatever current knowledge we have, right? So there is a balance that this reinforcement learning maintains. Like think of it as like how humans learn, right? A child, 2-year old touches a hot coffee cup or a mug, whatever, and then they find that this can hurt them next time. So they learned by like actually getting into the environment and then and getting a feedback. And because they were penalized with the like whatever hot they felt on their hand, and so they don't do that again, right? So that's the idea of reinforcement learning. And then there are other paradigms of learning that are like pretty I would say popular these days. For example, active learning, online, unlabeled, transfer learning, and big data. Let's quickly go over each one of them, like what they stand for. And so active learning is something that the person was like, and this is more related to like data collection, I would say. So it's a special case of machine learning in which there is an algorithm that is interacting with the user, right? And so to get some new label data points with certain outputs that are desired. So in statistics, it's also known as optimal experimental design. If you've taken any like statistics class, you might know that. So what's happening here is that like there's this like agent that's actively involved in collecting data to understand the problem better. So maybe the outcome, and not I wouldn't say maybe, but in many cases the outcome is going to be better than what we know because I'm like making an algorithm do that learning as we are collecting data. So obviously it's going to be better, but there is this challenge that exists and that might have come to your mind that the data cannot be considered IID, right? And so maybe we are losing the relationship between E in versus E out. So that's like the challenge with that. But then there are ways to deal with it. And in certain situations, as I said, is like because we have like this informed way of getting data. And so maybe we can do better in certain situations. So that's what active learning is all about. And then online learning. So again, and I would say active and online learning are in some ways related to reinforcement learning. They have that element of, interacting with something and then getting an outcome. So that's what's happening here. Well, online machine learning is a method in which data like becomes available in a sequential order. So learn as you get the data because you do not have the ability to store the data as such. So as data comes, you learn, act, move on. So you can see that there is like some relationship, with reinforcement learning because like based on certain outcome, based on certain actions, you are like learning and then moving on, right? So this is a common technique used in areas of machine learning where it is computationally infeasible to train over the entire data set, training set, or whatever, right? So it's like really important for the algorithm to adapt to new patterns in the data, and so that's why we do online machine learning. For example, stock prices prediction. All right. What is this transfer learning? Transfer learning is, I would say, think of like when humans, like for example, I know how to drive a car, right? And if I'm trying to learn to drive a truck, then I have some basic knowledge of driving, right? So I'm transferring that knowledge of whatever learning of my learning I have of driving a car, and so I can transfer that. So it's similar to that, transfer knowledge from some huge database that you already know prior to your like that is related to your problem, and so prior to starting learning that problem, you can transfer that data to this learning problem. All right. And then comes big data, the big buzzword, I would say, everywhere these days, big data. And so, of course, big data is not just related, the real problem here is not just being related to we have loads of data and then we need to do something about it. Of course, that's there. But then this loads of data or lots of data is not the actual underlying, I would say, issue with big data. So the issue here is that the data is so big that there is no way you would like not output the final hypothesis G, but then but is there some way that you are able to output your G without processing all the data? So basically, can you like sample down in some smart ways and not lose any information, right? Because the data is so big that I doubt you'll not be able to come up if you had the resources to go and like process everything in there, I doubt there will be a way that you will not be able to come up with the final hypothesis that's really close to your target function. But the challenge here is that we don't want to do that because of the price that we're going to pay when we are trying to kind of analyze, when we are trying to process this like huge data that is computationally intensive. We don't want to get into that because of the price that we are going to pay, right? And so that's the fundamental idea of big data and how to deal with it. All right. So this is how we are navigating the jungle. This is how we are navigating these three different, I would say, categories. And this is how we've like separated these different categories. So whenever you look at any of these, like you look at this big cloud of words, just go ahead and try to put them like under each of these categories, and then you will feel better about it. Trust me. Okay. So having said that, how are we going to move forward? That's the big question, right? And so how are we going to go ahead from here with whatever we have? So the good news is that you have the foundations, and even if you stop here and try to like move in any other direction with the advanced techniques, you should most likely be okay, right? Because you understand the theory is going to stay with us. It's not going anywhere. It is going to be applied to some advanced techniques. So in specific, the advanced techniques that we're looking at is number one, similarities, some similarity-based methods. In fact, I think the next lecture begins with the similarity-based methods, the nearest neighbor methods and all of those. So that's something that we're going to look at. Next comes the neural networks, deep learning, deep neural networks. So let's look at that after that, and then this, it's nothing but cascading linear models, and then support vector machines are more robust, I would say. Linear models in terms of the I would say methods under the techniques category. We look at pre-processing and aggregation, as I said. So this is something that's coming forward, and of course, as I said, theory is going to stay, but we're going to apply more advanced techniques and see how our concepts, our theory help us like in practice, right? Other learning paradigms that we're going to look at is unsupervised learning, a little bit of reinforcement learning, as I said, if time permits. Maybe we can have one full lecture on that. There is no way we can cover the entire thing. And of course, there are courses available where you cover entire unsupervised learning only and then complete reinforcement learning only. Unfortunately, we don't have all that much time, but we'll try to at least touch upon reinforcement learning. So that's it in this lecture, and then thank you so much for watching, and see you in the next lecture.